Hello, this is Ian, and today we'll be looking at an interesting question on nitrogen oxides from the ACJC 2017 promotional exam. So let us take a look at this question. So nitrogen dioxide is a brown gas that's formed in car engines, right? Thus resulting in various phenomena like acid rain and petrochemical smog. So the nitrogen dioxide molecule undergoes a resonance. So just as a recap, what do I mean by resonance is when the true structure of the molecule is best represented by average over multiple resonance contributing structures. So over here, these are the two contributing structures. So we expect that the true structure of nitrogen dioxide would involve a partial charge, or rather exactly, because these two are identical resonance contributed exactly minus half charge on each oxygen, and a partial double bond character of each nitrogen oxygen bond. So copy the NO2 molecule and draw a 2p orbital of each atom in NO2. Okay, so obviously the hybridization of nitrogen, because let us draw the structure of one particular resonance contributor first, because that's so much easier. So we note that the nitrogen atom is a radical, right? And so there's an unpaired electron over here. And so what is the hybridization? The hybridization is sp2, right? If a p orbital on the nitrogen, right, overlapping with the oxygen atom, right, to form a pi bond, and then the oxygen atom also stores a lone pair in the p orbital. So using a diagram in A part 1, explain why the NO bond in NO2 shows partial double bond character. And so it becomes very clear now why it has this partial double bond character, right? Because the lone pair on this oxygen atom can delocalize, can overlap. Firstly, it must overlap first with the pi electron cloud of the NO pi bond, allowing the lone pair to delocalize, thus causing the electron density in the NO internuclear region to be higher than expected, and thus resulting in a partial double bond character. So I won't write it down, right? And that is just the explanation for part 2. And let us take a look at part 3. The enthalpy change of formation of NO2 is plus 33.18 kilojoules per mole. So we are asked to draw an energy cycle using this information and using values from the data booklet to calculate the average bond energy of the NO bond in NO2. So let us first, because bond energies are for breaking bonds in gaseous molecules to form gaseous atoms. So I do NO2, or rather, because one NO2 molecule has two NO bonds, right? They should be equivalent. So we have half NO2 to form half N plus O, right? Half a mole. And so we take a look at how we can complete this energy cycle, right, using the enthalpy change of formation of NO2. Right, if you agree with me that this, right, is the enthalpy change of formation of NO2, which is a gas at a room temperature, standard conditions basically. And so the standard enthalpy change of formation of NO2 is plus 33.18 kilojoules per mole. Okay, and then we do know what is the bond strength of NN and the bond strength of OO double bond. So we can thus get the answer very quickly. The bond energy of the NO bond will be equals to minus 33.18 plus 1/4 times the NN triple bond strength, which, let me flip open my data booklet for a moment, would be 944 kilojoules per mole. And then half a mole of OO double bonds being broken, which is 496 kilojoules per mole. Right, over here we do see the extremely strong strength of the NN triple bond, which in fact, right, even puzzled the Nobel laureate Linus Pauling, right? But I'm sure that modern quantum chemistry methods have also discovered the reason for the exceptional bond strength of the nitrogen-nitrogen triple bond. Maybe I shall make a video on that in future. But then we can get the value of plus 451 kilojoules per mole. Okay, so let us take a look at the next portion over there. If you were to observe with me, the next portion over here would be that a dimerization of NO2 occurs, right? So draw the dot and cross diagram of NO2. In fact, you are already given the Lewis structure, so the dot and cross is very trivial to draw, if you agree with me, right? So what would be the dot and cross? Right, and over there we are done with our dot and cross diagram. So okay, using your answers, draw the structure at N2O4. So if you have two NO2 molecules, right? If you have two NO2 molecules, right? How would you guess they will combine? How would you guess they will combine? Well, it is most obvious that because they are radicals, right? The two nitrogen atoms on the separate molecules, right, each having an unpaired electron, will come together, correct? Will come together. Can I rotate this? No, I can't. Okay, never mind. I'll draw fishhook arrows, right? And then to show that they come together to form one molecule of N2O4. So, let's draw the structure N2O4. It is very trivial to draw. Right, drawing the formal charges as well for completeness sake. If you don't want to draw the formal charges, you can indicate the dative bond formation using an arrow. The shape about each nitrogen atom, as you can see, there are three regions of electron density, giving an electronic geometry of trigonal planar, and because there are no lone pairs, the molecular geometry is also trigonal planar. So let us take a look at the next part. At a temperature of 47 degrees Celsius and atmospheric pressure, so let me actually drag the question below, so giving myself more space. Okay, at the temperature of 47 degrees Celsius and atmospheric pressure, 0.50 grams of the above mixture at equilibrium occupies a volume of 190 cm3. Calculate the apparent MR of the mixture. Okay, so this is quite easy first part for 1 mark. So you agree will be the mass in grams divided by a number of moles. And number of moles can be calculated by PV over RT, right, using the equation PV equals to nRT. So atmospheric pressure 101,325 pascals, right? And volume is 190 cm cube, so convert cm cube to meter cube times 10 to the power of -6, and then divide by the ideal gas constant 8.31 and the temperature of 47 plus 273 Kelvin. So let me type this value into my calculator. That will give you a value of 0.00732397, right? Leaving things to 5 significant figures. So MR would thus be 0.50 divided by this value. And what you get? You get 69.1. Okay, so by considering the MR of both NO2 and N2O4, determine the partial pressure exerted by each gas. So if you were to agree with me, right, just now we said that MR, average MR, right, is the total mass divided by number of moles, correct? Total number of moles. So if you would agree with me, right, the total mass is contributed by the number of moles of NO2 times the MR of NO2 plus the number of moles of N2O4 times the MR of N2O4 divided by the total number of moles, right? And then you can get the molar. You can break out the molar fraction of each gas, right, out, and then times the MR of NO2, which is 14 plus 16 times 2 gives you 46, plus N of N2O4 divided by N total times 46 times 2 is 92, and that gives you the apparent MR of 69.1. And you realize you have two unknowns, right, which is the molar molar fraction of NO2, 46 of it, plus 92 times the molar fraction of N2O4 equals to 69.1. But you do realize that the sum, because there's only two components in the gaseous mixture, right? If I will double check it, what is the above mixture? Okay, so there's no other gases, so the sum of the two molar fraction will be equals to 1. So let us find so the molar fraction of N2O4 is simply 1 minus the molar fraction of NO2, and then we can simply solve a simultaneous equation to get (0.49783) for the molar fraction NO2, and that for N2O4 is simply 1 minus that will give you 0.50217. Okay, so wonderful. What did the question ask for again? Oh, it asked for the partial pressure exerted by each gas. So that is very easy, right? We are already just one step away from the answer. So the partial pressure at NO2 is simply the mole fraction, right, times the total pressure. What's the total pressure again? It should be atmospheric pressure, right? 101325 pascals. Did they ask you in ATM or in pascals? Okay, they never ask you what, they never tell you what units, then express in terms of ATM, right? Make your life easy, right? So it's just this ATM, and the partial pressure N2O4 is 0.50217 ATM. Okay, and there is some physical justification for using ATM instead of pascals, right? Actually, but we don't really have to go into that lah. And let us write the Kp expression for the equilibrium in B. So of course, what is the equilibrium? It's 2NO2, right? It's in equilibrium with N2O4, correct? So the equilibrium constant, right, in terms of partial pressure should be partial pressure N2O4 divided by partial pressure NO2 squared, correct? And what will be its value at this temperature, right? And state the units. Okay, very simply, it will be partial pressure N2O4 is 0.50217 divided by 0.49783 squared, correct? So you get 2.03 ATM minus 1, right? 2.03 per ATM. So that brings me to the end of my solution, right? I hope I was sufficiently clear. And yeah, actually not too difficult a question, right? Maybe the resonance may throw some students off if they don't have strong foundation in chemical bonding, right? The Hess's law cycle was pretty trivial to solve. And yep, basically even the equilibrium question, right, slightly unconventional, slightly unorthodox, but not too difficult nonetheless. And so thank you, and see you in the next video.